All right. Well, we had a pretty interesting question here, and a more interesting topic, I suppose. But let's go ahead and dive in and see what we think. The statement is, A, shallow water is non-dispersive. Waves travel at a speed that is proportional to the square root of the depth. Okay. So in deep water, however, the waves can't feel all the way down to the bottom. They behave as though the depth were proportional to lambda. Actually, the distinction between shallow and deep itself depends on the wavelength. If the depth is less than lambda, the water is shallow. If it is substantially greater than lambda, the water is deep. Okay? So, show that the wave velocity of deep water waves is twice the group velocity. In quantum mechanics, a free particle of mass m traveling in the x direction is described by the wave function capital Phi x of t is equal to a e to the I px minus et over h bar, where p is the momentum and e is equal to p squared over 2m is the kinetic energy. Calculate the group velocity and the wave velocity, which one corresponds to the classical speed of the particle. Note that the wave velocity is half of the group velocity. Okay, so that's pretty interesting. Okay, well, let's dive in. Not that long of a question. So, with this model given, let alpha be the constant of proportionality, since the speed is proportional to the square root of the wavelength. Then we have v equal alpha square root of lambda. Color coordinated that. We have v in red and lambda in blue, but we know that v is equal to omega k, and that's equal to alpha times the square root of 2 pi over k. And once we substitute those in, we could solve for omega, so multiply k over. We see that if we substitute or push the k through to the square root, we can have a k squared in the numerator, cancels in the denominator. So omega is equal to alpha square root of 2 pi k. All right, so the group velocity is equal to d omega dk. And so if we take the derivative here, we see that we get alpha times 1/2, 2 pi k to the negative 1/2 times 2 pi. Just chain rule it out, power rule all the way through. We see that we get a cancellation here. If we push the 2 pi back in to the 1 over 2 pi k in the square root. And we see that cancels the 2 pi in the denominator down. And we see that we once again get 2 pi k in a simplified form, and that is equal to lambda, which again color coordinated. So what we see here is that this is equal to 1/2 v. Therefore, v is equal to 2v group, or twice the group velocity. So B, compare this wave function with the plane wave. So if we do that, we see that the exponentials are set equal. Again, coefficients will just take care of themselves. And if we look at that, we see that we have I times px minus et over h bar, and we're color coordinating this, is equal to I kx minus omega t. So what this says is that k is equal to p over h bar, and omega is equal to e over h bar. But e is equal to p squared over 2m, so we push that through, and now we see that p is equal to k times h bar from above after form matching. So we push that through, and we see that omega is equal to k squared h bar over 2m after all the cancellations. So from the fact that v is equal to omega over k, okay, and we know what omega is now, and we know what k is, we can show that that's equal to, canceling that through, we get e over p, or p over 2m, or is equal to h bar k over 2m. Both are completely, or all of those are completely the same. So the group velocity, though, again, d omega dk, we take that derivative, we get a factor of 2 up front, or a factor of 2 from the chain or product rule, can't speak. That simplifies to k h bar over m, which is equal to p over m. Okay, so again, this shows that v is equal to 1/2 vg. Okay, with that, since p is equal to mvc, or classical, where vc is the classical speed of the particle, it follows that vg corresponds to the classical that follows the VG corresponds to the classical velocity. Oh, man, this is it's working. But, yeah, pretty cool stuff.